Welcome, welcome, welcome. Welcome to your first webinar after half term. Actually, maybe not your first webinar, your first science webinar after half term. It's brilliant to see so many of you coming in already. I'm just going to get my screen set up and I will share it for you so you can see. Yeah. So hello all. It's absolutely brilliant to be back doing webinars, being back in sort of school mode. I know maybe not all of you may feel exactly that way. Some of you may be a little bit knackered. Maybe your sleeping pattern hasn't been brilliant over half term. But I can speak for myself and probably miss when I say that I'm really glad to be back in some sort of routine. I enjoyed my rest, but now it's time to get back on with work. So this week, what we're going to do is we're going to learn about something that's probably completely new for most of you. And it's a scientific principle called Le Chateliers Principle. Now, you are going to hear me mispronounce that probably about 6-7 times during this webinar, because honestly, I really do forget how to pronounce it constantly. But luckily enough, you don't have an oral exam in science, so it's just about knowing what it means. Now, in this webinar, what it's important to note is that this may seem a little bit confusing to begin with. And when I start to introduce these topics, your instant reaction may be, oh, wait, what? And what I want to reassure you is that this week, I'm going to take it really slowly. The topic itself is actually quite small. Le Chateliers Principle is, you know, it's about that much that you need to learn, really. But I'm going to go over it nice and slowly and make sure it's really well embedded. The questions that you've got this week are all about this. In fact, they're going to seem really repetitive. And that's because those questions come up really frequently in exams, okay? Really, really frequently. So you don't need to know much, but it is a little bit difficult to get your head around. There's also some additional videos in here for you to watch later on to help you. So let's start by doing a little poll. Let's get ourselves a little bit warmed up. And I'm going to launch a poll where I just want you to answer some questions based on things that we've gone over in previous webinars. So exothermic and endothermic reactions, rates of reactions, some things about catalysts in there and concentration. Have a go, really think about all these questions, and that'll give a little bit more time for those of us who are slowly getting into the webinar to join. Remember, guys, I don't know who submitted what response, so don't be worried about getting things wrong. Have a go. It's really important that you try so I can see where we are so far. So I'm going to give you 2 minutes. You've got about 1.5 minutes more. Okay, good. I'm starting to get some results in, which is brilliant. And some of these questions you'll recognize as being ones that I've asked you before. And that's really great that I can already see much improved answers, which is great. Brilliant, brilliant. Got about a third of you have submitted already. We've got about 40-50 more seconds, so I want to see as many of you have a go. Okay, just about 10 more seconds left. And then we'll go through the answers really quickly, and then we'll crack on with Le Chatelier's principle. Oh, can't see the last two on question 4. Well, the correct answer is one of the first two, so that might help you. Okay, brilliant. So I'm just going to end the polling there. I know a few of you have just last minute submitted things. But let's have a little think about what the answers were. So firstly, what is an exothermic reaction? Brilliant that the majority of you did in fact pick the correct answer, which is where temperature rises due to energy being released to the surroundings. Okay, remember, energy is absorbed in an endothermic reaction and energy is released in an exothermic reaction. So when you think exothermic, you should think temperature rise and release, because those are the things that will get you the marks in the exam. Increasing pressure increases rate of a reaction because particles are closer together. Brilliant, well done. We know that that's because the container is getting smaller often, and that means that the particles are close enough to react. Concentration, brilliant. Number of particles per unit volume, really important definition, and a really easy one just to try and remember. Difference in the rates of reactions on a graph. The higher the rate of reaction, the steeper the line. They will end at the exact same point, so they'll both eventually flatten out and will reach the same level on your y-axis, but they'll get there at different speeds. What does that symbol mean? It is, in fact, you're absolutely right, a reversible reaction. It goes both ways. The arrows go both ways themselves. A catalyst increases rate of reaction by lowering your activation energy. If that's something that you're still a bit confused by, I would suggest going back to previous videos and having a little look at some of the graphs. Dynamic equilibrium. This is one that we covered a couple of webinars ago. And the definition of dynamic equilibrium is where the rate of the forward reaction is equal to the rate of a backward reaction in a closed system. Okay, so the rate is equal. Forward and backward is equal. Okay, and often dynamic equilibrium, that comes up as a single mark question or as a 2-mark question where you have to write down the correct definition. Okay, so well done. That's good to see most of you getting those answers absolutely correct. Now, the work for this week, ladies and gentlemen, will be just as we've done before. You're going to watch this video either live, or some of you will have to be watching it back, or both. There is a video embedded in the slides that I'm not going to have time to show you today that I would like you to watch because it further solidifies what you will know. You then have a quiz and some longer answer exam questions that hopefully I'll get to show you at the end of this. One thing I do want to reiterate, guys, is that there is a clinic for Year 10 higher students on Friday at 10:05. So if you have a go at the questions and you're struggling, that is something you can drop in and you can ask questions based on your work if you get stuck. Okay, so that's just something that's there for you in addition to this webinar. Now, if for any reason you still feeling a bit wobbly, that poll, maybe you didn't do so well, maybe you're still not 100% on those ideas, I've put this slide in here just to direct you back to some of the previous work we've done if you need to go over it. Now, let's get started with today's work. Now, the first thing I want you to do is to imagine. Imagine that you are a chemist. Now, when I say chemist, ladies and gentlemen, I don't mean a pharmacist. A pharmacist are the people who work in chemists, and they are chemists, but we're going to talk about industry chemists. And as a chemist, you are focused on making something. That's your area. Now, you might be involved in the production of fertilizers. That's these things that you add to plants and crops on a large scale to make them grow better and more quickly. And that's a huge area of chemistry, guys. That is a multi-billion-pound industry, okay, making fertilizers. You might be in the realm of making catalysts. When we talked about catalysts, we talked about the fact that the university I went to, they do a lot of really good research for gold as catalysts. You might be a chemist who works in formulation. You might work to make cosmetics, okay? If you wear makeup or you wear skincare or you use shampoo or any of those things, there is a chemist out there who has come up with that formulation. Or you could be working in pigments, so things like paints and colours. Again, it seems like a strange industry, but actually it's all part of the chemical industry. So for the rest of this webinar, you are going to be thinking as an industrial chemist. You are making something. You can think about whatever way you want to. You could be a fertilizer chemist, you could be a makeup scientist, whatever, but you are thinking about making stuff. Now, in the chemistry industry, in your industry, when you go about making your product, there are two things that need to go through your head. I want to make as much product as I possibly can and do it as quickly as possible. Now, you also want to think about doing it as cheaply as possible, and we'll talk about that later. But the two things we're going to focus on, and we need to make a distinction between, are yield, which is how much product you make, and rate, which is how quickly you make that product. Now, if I have a giant lab, if I can make as much product as possible, if I have a really high yield, I'm going to be able to sell more of it. So therefore, I'm making more money, and that's brilliant. If I have a reaction that goes very, very quickly, that has a really high rate, well, I'm using less energy most of the time. I've got to pay my staff less because it gets done in a quicker time period. I've got a greater yield in a shorter amount of time. Again, I'm making more money. Happy days. So these are the two things we're going to think about today. And we've already done a lot of work on rate. We've talked a lot about how to increase the rate of a reaction, and that is brilliant. But what we're going to focus on today in detail is how, as chemists, we can increase our yield by changing our conditions. Similarly to how we change them for rate, now we're going to change them to try and make as much product as possible. Now, before we do that, I just want to see how well we know the definitions of those two things. So I'd like to have a go at this very quick poll. There are only two questions. Define rate of reaction and define yield for me. Really thinking about this, because if you don't know this, if you don't know the difference between these two things, the rest will be a little bit more difficult. So think about it before you write, before you click. So 2 questions. Let's go, guys. 30 seconds. Let's go. What is the rate of reaction? What is the yield? Good, excellent. 20 more seconds. Right, 10 more seconds. Get me an answer. Jump something in there. What is the rate of reaction? What is the yield? Okay, brilliant. So I'm going to end polling there, and let's just go through this really quickly. So a rate of a reaction is a measure of how quickly either your reactant is used up or your product is formed. Okay, we looked at that when we looked at rate. So rate is to do with speed, and it's to do with how quickly either you use up what you start with or you make the stuff that you want in the end. Yield is the mass of a product made in a reaction. It's nothing to do with speed. Okay, yield is to do with how much stuff you get out. Okay. Now, the last option on yield was percentage of reactants converted to products. I put that in there because we eventually, later on in chemistry, will start to look at that, or start to look at how we can predict how much is going to be converted into a product and how we can calculate how much has been converted. But yield on its own, actual yield, is how much is physically made. So when you weigh something at the end of a reaction, how much have you got? Okay, so that's the difference. Rate is speed, yield is how much you've made. Now, Le Chateliers Principle, I told you I was going to say it wrong. Le Chateliers Principle is about how we can change the position of equilibrium in a reaction. And the definition itself is in bold and it's italicized underneath that. When change is made to a system at equilibrium, the position of equilibrium moves to counteract the change that was made. Now, that's your definition. And I'm going to be honest, I don't see many questions in the exams that ask purely for a definition. It's more about how you can apply this concept. Now, you're probably sitting at home reading that going, what does that mean? Because I would agree that it's not very clear from this definition. What we'll do is we're going to see what it means in application, and then we'll come back to it. So when a change is made to a system, the equilibrium moves to correct the change. Okay. when we talk about changing a system, we're talking about changing the conditions of a reaction. So doing something that changes the amount of products that are going to be made in one way or another. So when we talk about equilibrium, ladies and gents, we're talking about a nice reversible reaction like that that's balanced, okay? So when we talk about equilibrium, we will tend to just draw a reversible reaction. And you can tell that this is something that can reach equilibrium because it's got that reversible reaction sign. As a reminder, equilibrium just means it's reached a balance, okay? It's a fancy word that we don't need to define right now. Now, we know already that in dynamic equilibrium, the rate that A and B are made is the same as the rate that C and D are made. So the reactions are equal in rate in both directions. We also know, because we looked at it when we looked at reversible reactions, that if a reaction is exothermic in one direction, it's endothermic in the other. Now I've put this up again. This is just recapping because we're going to need this for the next thing we do. Now, when you get a question about how we can change the position of equilibrium, and what I mean by that is the reaction going to go in the forward direction more, or is it going to go in the backward direction more? For example, is it going to make more of C and D, or is it going to make more of A and B? The way that I can affect that and change that is to do with these three things. These three things are the things that we need to think about when we think about changing the position of equilibrium. Temperature, do we increase or decrease temperature? Pressure, do we increase or decrease pressure? And concentration. If I increase the concentration of one thing in the reaction, what will happen to the position of equilibrium? Now, as I go through each of these, I'm going to take you through it really slowly, and then I'll pause, and if there are any questions in the Q&A, we'll do them after each part so that we don't have a mountain of stuff at the end where people don't understand, okay? So first of all, let's think about what equilibrium actually means. So if I said to you, the equilibrium is moving, or the reaction is moving in the forward direction or to the right, what I'm saying is that more of products C and D are being produced. So if the equilibrium shifts to the right, and I know I'm mirrored, but to the right, the direction of the arrow pointing, then we know that it's going to this side here. If equilibrium shifts to the left or in the backward direction, then more of A and B are being produced. Yes, Soren, you're right. So more of A and B are being produced if equilibrium shifts to the left. So the shifting is to do with which side of the reversible sign am I on more frequently? How much of that product is being made? Where's the yield going to be highest? Okay, so that's something just to remember for now. So temperature changing in equilibrium. An increase in temperature will always cause the equilibrium, the reaction, to shift towards the endothermic direction. And that is because an endothermic reaction is one where heat is absorbed. If I'm heating a reaction up and Le Chateliers Principle says that equilibrium is going to try and counteract that, well, it's going to try and absorb that heat so the temperature doesn't increase too much more. Okay, so that's why the endothermic direction is the one that you see more predominantly, the one that is favoured. So what does that mean, right? What does that actually mean when you're in an exam or you're looking at a reaction? Well, if the reaction is exothermic in one direction and endothermic in the other, as we already know, if I were to heat up this reaction, so I had these reactants A, B, C, and D in a jar, and I added heat. Well, the heat is going to favour the endothermic direction, 1 mark. So the equilibrium shifts to the left, 2 marks. That means you have a higher yield of A and B because it's in the endothermic direction. Let's think about the other way around. It doesn't often happen, but let's think. Imagine I lowered the temperature. Well, by lowering the temperature, the equilibrium is going to try and counteract that by trying to release some heat to keep it balanced. it's going to go in the exothermic direction. If it goes in the exothermic direction, it's going to favour the right-hand side. So the equilibrium is going to shift to the right, which means you have a greater yield of C and D. Now let's get this really, really straight. This reaction in the forward direction in the right-hand side is exothermic. So therefore, if I give it lots of heat, I'm going to make more of A and B, okay? Because the equilibrium is going to shift over to that side, all right? Do I have any questions about that just for now? Anything about temperature and equilibrium? So I increase temperature, it goes to the exothermic direction, the endothermic direction. I knew I'd do that. Now, if this reaction wasn't exothermic in the forward direction and it was endothermic, it would go that way. Whichever way is endothermic, it will go. And the exam question will tell you that. Okay, I'll show you some examples later on. So increasing temperature will shift the equilibrium to the endothermic direction, and that increases the yield, the amount of stuff that's on that side. Okay, we'll see some examples in a little bit. I'm going to use an example of the Haber process, which is a really important process in industry. So that's temperature. That's something we need to remember. Let's look at pressure. Now, before I start with pressure, I am going to be really clear that this is the one that people get wrong because they get it a bit confused. So bear with me, okay, and really listen. So an increase in pressure will cause the equilibrium to shift towards the direction with the fewest molecules, not the fewest atoms, the fewest molecules. I'll show you what that means in a second. Now, in your exam, sometimes they won't use the word molecules, sometimes they'll use the word moles. And we will go into moles. If you've already done a little bit on it, fantastic, but we'll do much more on moles at a later date, okay? But just so you're aware, that's the change in the language. Now, the reason it goes toward the side with the fewest molecules is, imagine you're banging up the pressure. Well, it's going to try and go to the side to sort of relax that. You know, let's go to the side where there are less molecules so that there's less pressure, okay? It's trying to counteract the change. So let's look at an example. You've got this reaction. 2A plus B goes to 2C, and it's a reversible reaction, okay? Now, if I increase pressure in this reaction, the equilibrium shifts to the right, to the forward direction, because there are fewer molecules on this side. If I were to decrease pressure, it would shift to the side with more molecules to try and get that pressure a little bit up again. And that side has the side with more molecules. Now, notice I said molecules, not atoms. You can see how many molecules there are by counting the big numbers. So bear with me on this one. Over here, I've got 2 lots of A and 1 lot of B. Now, there would normally be a 1 there, but you know, in algebra, guys, if it's 1, you don't put the 1. Don't worry about it. So 2 lots of A and 1 lot of B gives you 3 lots overall. After the reversible sign, there are 2 lots of C. So if you've got 3 lots and 2 lots, 2 lots is the side where there's fewer. Okay, so we're going to shift to that side. So increasing pressure, 1 mark. Well, actually, no, that's not the mark. Increasing pressure is going to shift the equilibrium to the side with the fewest molecules, 1 mark. In this case, that's to the right or in the forward direction, 2 marks, which is going to increase the yield of C. I'm going to make more C, okay, because that's where the equilibrium's shifting towards, okay? So the yield increases of C if the pressure is increased, okay? And that's your 2 marks, but if it was 3 marks, you would also talk about why. Any questions on this so far? So we've done temperature, endothermic direction for an increase. We've done pressure to the side with the fewest molecules. And we're going to go on to concentration in a second. And then I'm going to show you how you might be asked some questions about this. Okay, it might be because there's quite a few of us, we don't want to ask questions all together. That's absolutely fine. I'll hang around at the end anyway, and you can ask your teachers specifically too, because I know this can be a bit tricky. Right, so the next one. Ooh, brilliant. So somebody Soren in the Q&A has just said, to work out which side of the reaction equilibrium goes, can I think of weighing scales? Yes, with pressure and concentration, yes, weighing scales is a great idea. Okay, so if there's more molecules on one side, that means the weighing scales are tipped down one end. How am I going to get this side down? Well, I'm going to shift equilibrium toward the side where there's less to try and balance it out. Brilliant idea. Someone said about the why. Let me go through it again. You're absolutely right. So the first thing you would say in the exam is what is going to happen. So increase in pressure means that the equilibrium is going to shift to the right in this case, okay? Because the why is because that is the side with the fewest molecules or fewest moles. That's either of those two things is fine. Therefore, so your final point would be about the fact that the yield of C would increase. So someone's raised an interesting question. What if you increase the pressure, but it's already on the side with the least molecules? So the equilibrium is already favoring that side. It would just favor it more. You know, it's still going to move towards the side with the least molecules. Okay, and we're going to look at an example in a second to help understand this a bit better. Really good question, Jiten. Really impressed. So let's look at concentration and then we'll look at an example. Now, concentration is, I think, the easiest one. I'm going to read you the proper definition. I'm going to tell you the easy way to remember it. So what happens when you change concentration? So an increase in concentration of one substance in your reaction will cause the equilibrium to shift to the other side. So if I increase the concentration of one of my reactants before the reversible arrow, it will shift towards the other side. So kind of like pressure, it goes to the side where there's less. This is to try and counteract that change, to reduce the overall concentration. So if I increase the concentration of B in this reaction, in which direction, to the right or to the left, will my equilibrium shift? You tell me. So I'm going to increase the concentration of B. Which direction, right or left, forward or backwards, either way, I don't mind, is the equilibrium going to shift? Good. I'm getting some good answers. I want more. I'm greedy. Fantastic. Excellent work. So the really easy way to remember this is it's the opposite side. So it moves to the other side. So if I increase the concentration of B, it's going to move to the side. The equilibrium is going to shift to the side that's not had the increase, and therefore the yield of C and D will increase in this case. If I increase the concentration of D, so the other side here, the equilibrium is going to shift to the left. And that's because it's going to try and counteract that change. So it's going to shift to the left, and I'm going to have a higher yield of A and B. So that's concentration. I think it's the easiest one because it just shifts to the other side. So I'm going to do a quick poll now, and then I'm going to show you a really specific example that will help you understand it, I think, and I think really sort of nails it all in. So let's have a quick go at the poll.